Hey everyone. So, with the test coming up very soon this week, I decided to make a last minute kind of review going over the substitution and elimination reactions, and then doing a little bit of problem set practice. So, I'm going to do a very brief overview of the different types of substitution and elimination reactions, and then jump straight into the problem set. So, if you want a more comprehensive overview, I recommend watching either Derek's video or Dr. Berg's lecture videos on the types of reactions. I'm just going to go over some really key points to start off with. So, with SN2, it's basically just a substitution of our leaving group. A lot of times it's like a halogen, bromine, things like that, with a nucleophile. That's going to be a lot of times a weak base, could be strong base in some situations. So with SN2, a really big thing to remember is that stereocenters generate inversion of stereochem. So if you have an R molecule, like we look here, um, or in this case, we have a molecule with an S on it. So if we number our group, since we have a chiral center right there, we get S, and then we react it with a weak base. So NaCN is one of our weak bases, acetone just being the solvent. And then when we do that reaction, we get an inversion of the stereochemistry to R. So just being careful when you're doing SN2, if you see stereochem, um, you're going to have that inversion. That's where your leaving group is. So being very careful with that. So kind of another thing with our SN2 is that they occur with, we call it zero prime or just a methyl group. Very common there. We have our one prime alkanes, and we have our two prime alkanes. Three prime is really not gonna do substitution, and a lot of these things, when we're trying to like figure out what things do what with like what types of bases, I would refer to that chart. Very important for the test. You need to know that pretty well. It's gonna be a big portion of the test, knowing how to do the reactions, knowing what molecules do what with which types of base, if it's a strong base or a large strong base, small strong base, and being able to tell the difference. So I'm not gonna go over that here, but just make sure you know that for the test. And something else, so a weak base are always S and 2 because they're um so weak, they don't really have enough strength to kind of like pull off that hydrogen and a leaving group to do elimination. So they're only ever going to do SN2. So basically, I would recommend trying to learn the small strong bases, large strong bases, and then your solvents, and then basically everything else is weak base. So a lot of times it's like Na and then something else. So like in this case, NaCN, and then you have like NaSH is another common one. And kind of be able to recognize it that way. But just knowing like which ones are which are really important for the test. With that, so the strong bases can sometimes do SN2, although they're more likely to do like E2 or something like that. So now kind of moving on to SN1. So with SN1, we're gonna get the only difference really here is the formation of a carbocation intermediate, which does not happen in SN2. So with that, there's no stereochem. At least in the fact that in this case you'll get a racemic mixture of your product. So if you do have stereochem, you'll get a product that's R and S, if that makes sense. So you get one that's R and one that's S because it can rotate because with the carbocation formation, shift can happen, which can affect one where it adds if you have the opportunity to shift to a more stable carbocation, like so if it goes from a two to a three, that's where that group's gonna substitute or gonna add on to, even though um, the original leaving group was not there. You can shift just like some of our mechanisms that we had for test two. So just recognizing that and remembering what carbocation shift looks like is really important here. Another thing with SN1, when you're doing these, you're only gonna really like see a solvent, one of those like um, either aprotic or protic solvents or something like that. Dr. Berg's asked you all to learn. And so it's going to be that plus a temperature. And in this case, SN1 likes to happen at low temps. For example, like 0 degrees Celsius, something like that. Pretty low. This reaction's kind of slow, just kind of like slowly happens, but this is what it prefers to do S1. Like I was saying earlier, just need to remember it forms that racemic mixture of enantiomers. So with that, it'll be like more so with the stereochem. So I guess with the no stereochem part, the stereochem doesn't matter as much. You're not gonna have an inversion, you're gonna have both. So it'd be like R plus S products. So I would not focus too heavily on the no stereochem part that I mentioned before. I would focus more on the fact that you're gonna have a mixture, but that there's no like change necessarily. So now kind of moving on to our elimination reactions. So our elimination reactions are basically the opposite of those addition reactions that we learned for test two, like the addition of HBr, the addition of Br2, CH2Cl2. So these eliminations help, or these reactions help remove groups like that by taking off that bromine and then a hydrogen along with it to form a double bond. Or in some cases, we have a certain reaction that can form a triple bond, which is very helpful for synthesis. It's the NaNH2 and then NH3 on the bottom with negative 78 degrees Celsius. One of the most powerful eliminators that you will learn in OChem and very important for the test. So going into elimination, we have E2 and then E1. So with E2, we have a couple of different possibilities that E2 can do. So first off, we have E2 Zaitsev, which is basically just the more substituted elimination. So if we look at something like this, and we have our bromine right there, and then it's E2Z, whatever base we would need for that in this case, and we eliminate. So Zaitsev would look something like this. Go into that center because it's 2' 2' there. Then we look at Hoffman or E2 Hoffman, E2H, however you want to call it. It's the less substituted elimination. So just knowing the difference between which bases do E2Z, E2H, depending on what type of alkane you have, if it's a 1', 2', 3', so on and so forth like that. So an E2H would look like this. So put that bromine on the same group, like that right there, E2H, and then it'd be like that. It'd go in the other direction rather than towards the more substituted carbons. It'd go to the end with the least substituted carbon. And then we have unspecific E2. So this just basically means you have a certain type of alkane with a certain type of base that when it does elimination, it's only going to eliminate in one direction. It doesn't really have any specificity. There's no way for it to choose between E2 and E8, E2Z and E2H. So for example, write this out first and then. So if we draw this same type of molecule like this, but then we put that bromine right there on the end, and then we do E2. There's only one place for that elimination to happen, and it's going to look in this case like a Hoffman elimination because it's not on the more substituted carbons, but it's not Hoffman. It's just the only way it can eliminate, and it's going to look like that. So just be able to like recognize which bases do what eliminations off of what type of alkanes, very important. Then moving on to the anti-periplanar aspect of elimination, especially with E2 elimination. So when you have stereochem, like on a ring especially, it's very easy to see like this. So our bromine right there, we're looking at on that dashed, those dotted dash lines. And so when you have it like that, you have to have a hydrogen on one of your beta carbons. So we can start with that. So our leading group is always on our alpha carbon right there. And then the carbons directly surrounding that carbon are our beta carbons. So then we have to look at our beta carbons to decide, okay, which one of those carbons has a hydrogen that can be that's anti-periplanar to our leaving group. So in this case, we need a hydrogen that's on a wedge. So we're not going to look at the hydrogen on the alpha carbon. We're going to look at, we can call this beta 1, and we'll call that beta 2. So in this case, we look at beta 2 first. Beta 2 has that methyl group on a wedge and then a hydrogen on the dash. So that hydrogen can't be eliminated because it's not anti-periplanar. And then that methyl group, it's not a hydrogen. We can't really eliminate methyl group. Not going to happen in this case. So we're going to go down to B1 and say, okay, there we go. We have that hydrogen on a wedge. And that's what we mean by anti-periplanar. Just so if you have a dash line kind of saying, okay, that's going away from whatever structure there is, and then that solid wedge is kind of like saying, oh, it's coming towards you in a way, or however way you want to look at it, so that you know that they're opposites. That's basically what anti-periplanar means, at least in this case when looking at a wedge. So if we did elimination, this would be the structure that we get. Like that. And so when you form that double bond, it kind of it takes away the stereochem here completely, and then also up there because of the double bond. But at the very top piece, you need to make sure to redraw that stereochem because it's still there the way that it was with the original. Now, kind of moving on to E1, this also forms a carbocation intermediate the same way that SN1 does. And something to know for this is that E1 is always Zaitsev. So it's always going to do that more substituted elimination if possible, which makes sense with the carbocation. It's going to go towards that more substituted section. So, like with SN1, shift can happen, and it's just something important to keep note of. Make sure that you're aware of that. Now, SN1 happened at low temperatures. You had your solvent. So in this case, we're also going to have just our solvent. And in this case, we're going to have high temperatures. So when I say high temperatures, I'm kind of meaning like 50 degrees C and above. So 50 is a good mark if you just remember a solid number. 0 for SN1, 50 for E1 is a good way to do that. So when you're doing either filling out the table or looking at the reactions page on the test, make sure you're taking note of the temperature if there is one with just a solvent present. So hopefully that was some quick review over some basic things for the reactions that you need to like be aware of and like little things to look out for. But now we're going to move on to the problem set and kind of go over some of the reactions like you will be seeing on the exam and stuff. So with our first one up here, we have a 1' alkane like that with our bromine on the end. And then we have a small, strong base. I know earlier I said if you see that Na, a lot of times it is a weak base, but you also have to take note of, that's why I said learn the small, strong bases because then you would know immediately that this one is one of those small, strong bases, not a weak base, pretty much. Um, and to kind of like break down reactions in general for this test, I recommend label your base. Label, okay, is that a 1', 2', 3'? And then that kind of like, you can kind of think of the table in your head or either draw it out, whatever works for you. And you can be like, okay, I know that a 1' alkane with a small strong base is going to do substitution. So in this case, we're going to have an SN2 reaction. And that's just from knowing the table, being able to connect the two. And then, so our leaving group is basically like on the bottom, we have the CH3OH, the CH3ONA on the top. The Na is just kind of like stabilizing that group. So our actual substituting group is going to be that OCH3, and that Br is our leaving group. So when we draw our product, it's gonna be just like that. Just substituting, swapping the groups, um, just like that. So I'm moving on to the next one right here. We have another one prime. Always a good place to start. This is one of the most common large strong bases right here. You will see this one a lot. It's one of the easier ones, at least for me, to like remember. It's a CH33. It's a relatively large structure. Kind of makes sense when you're looking at it this way. But so, like I said earlier, with a one prime or with the strong bases, sometimes it can do SN2, but large strong bases are going to want to do elimination. So in this case, we're going to have um, elimination, but it's going to just be E2. And that's kind of like what I was mentioning earlier. That's a one prime alkane. It's only going to eliminate in this direction, pretty much, because it can't go the other way, obviously, because there's no more carbons. So when we're looking at our product, it's something like this, just like that. Now, if the bromine was maybe a two prime here, then you can start looking at E2Z and E2H because it could either go in that less substituted direction or the more. But when there is no option, know that it's E2. That's important for the table. There are a couple reactions like this one that do E2, and that's a point he could potentially trick you on. If you write E2H, E2Z, you unfortunately won't get a point for that one. Another like little mistake a lot of people make is with the carbon chain. Always keep your same number of carbons. So if you have one, two, three, four, five carbons there, make sure you have one, two, three, four, five carbons there so that you don't lose unnecessary points. Like if you get to do the reaction right, but then draw a four carbon chain, depends on who's grading. If you get the credit, because they might think you eliminated a carbon for some reason. So just being very careful with that. So moving on to the next one, we kind of have somewhat of a special case. Fluorine is one of the worst. It's a pretty bad leaving group. And with a bad leaving group, it's like this reaction itself, you would think that it's going to be E2 Zaitsev because we have that 2 prime right here. We have a small, strong base. I'm pretty sure if we look at the table, that's going to show E2 Zaitsev. But with a bad leaving group, it's actually going to want to do E2 Hoffman. So looking at E2 Hoffman, we know that that's going to eliminate to the to the less substituted position. So we draw out our carbon chain again, making sure to retain the same number of carbons. And then in the less substituted direction would be right there with that double bond. So now kind of moving on to a couple other types of reactions. So over here, we have a stereocenter, so that makes the potential for a inversion to happen if this is SN2. So and immediately we can say, okay, this is one of those weak bases because it's not a small strong base, not a large strong base, not a solvent. So we immediately know that it's a weak base. So we're like, okay, as soon as you see that and connect those dots, we're looking at an inversion. So take a note of that just so you don't forget why you're doing it. And just continue labeling. So we have 2 prime there. And then we can kind of like label our stereocenter. So label bromine 1, our chain over there 3, or 2, sorry. And then our methyl group being 3 right here. So when we do that, rotation wise, we get R to start with. So this stereoisomer is the R isomer. And when we do the reaction, we basically are going to substitute the groups so that our stereochem changes to S. So you can keep that H going up like that. But now we're going to have that methyl group coming out like that. And then the group that we substituted, our SH group, coming out like that. So then if we number, our 1's going to be here, 2 there, 3 there, and of course our hydrogen is our 4th group. And then if we look at this and do our like rotation, whatever works for you to figure out R and S, this one's going to give us S. That's pretty much all that you have to do with this one. Substitution itself is some of the easy reactions, but just not forgetting that with SN2, inversion can occur. Kind of moving on to the next two. These are some implementation of the anti-periplanar rules with elimination. A lot of times you will see this on a ring like this. It's very common. So when looking at this first one, you see that our bromine right there is on that dashed line. So with that, we need a H on a dash. So, and I guess to go back a little bit, we know that this is a small, strong base. This right here is a 2' carbon, and that's going to give us E2 in this case. Since there's only really one direction for this thing to eliminate, it's going to go in that one direction. So I'm just going to call it E2 in this case. So when we're looking at our hydrogens, we can look at this, look at our beta carbons. So here's our alpha. Here's beta, we'll call it beta 1, we'll call that beta 2. So beta 1, we have a hydrogen on a dash, so that's not going to be it. That methyl group, not going to eliminate that. When we look down here at beta 2, okay, that hydrogen on the dash, unfortunately, is not it. However, this one, this hydrogen right here, is perfect because it's on that wedge, so it's in the opposite or the anti-plane of the bromine. So then we're eliminating. We're just drawing it out normally, just like this. This is very similar to the example I just did in like the review part of the notes. Making sure to keep your stereochem up top here, like that. And then down the end piece right there, the stereochem is gone because of the double bond. There's no chiral centers possible there with an sp2 carbon. So now moving on to the next one. So when looking at this, it's kind of a very similar problem. We have a small, strong base. This time we have a 3' carbon. And then if we label, this is our alpha. And then these are our betas. We'll call that beta 1, beta 2, beta 3. So a lot of times people don't realize that this carbon is actually it's a beta carbon, even though it's not in the ring. It is one of the ones because it's directly connected to that alpha carbon. It's able to be eliminated like that. And now we have to start checking those hydrogens. So we need a hydrogen on a wedge. So no there, no there. Can't eliminate a methyl group, can't eliminate that methyl group. So then it leaves at B2. So now we either are going to have no reaction, or can we potentially maybe eliminate one of those hydrogens off of the CH3? And so if you kind of draw this out, let's see, we'll do this in orange. So this carbon right here is representing this carbon. And then, so we have an H, an H, and an H. This is like a way you can look at it. So since that carbon is on that wedge, has that stereochem, you can kind of like see it as, okay, at least one of the hydrogens on that carbon is going to be in the correct plane, like the opposite plane, which makes it possible for elimination. So in this case, this one right here is on that wedge, which is exactly what we need for our elimination. So we're going to take one of those hydrogens off right there, keeping our stereochem up top, as well as down here this time, because there's a double bond between those two. It's between the alpha carbon we had and then the methyl group. So hopefully that was helpful for those reactions. For the bottom part, just kind of like seeing, so this goes back to for the constitutional isomers, um, kind of E2Z versus E2 Hoffman. I'm not going to go over these two. Give you a little bit of challenge, not do all of them for you all. Um, but these are good for like understanding that, okay, I can potentially have isomers with elimination, or even substitution reactions. These are both eliminations in this case, but showing that with the first one, if you eliminate Zaitsev versus Hoffman, you have two different molecules, or constitutional isomers in this case, because they are in different spots, they would have different names, which is a clear indication of a constitutional isomer. And then for the last one, stereoisomers think, okay, RNS is a big thing with stereoisomers, E and Z with alkenes, another big thing. So when you're doing that one, look at where you're eliminating, um, and then seeing, okay, what products do you get? And then a lot of times stability is a big issue. So which one is more stable, which one's more substituted, which one has large groups far apart so that you don't have that steric hindrance. Those are the two really big things kind of for these last two problems at the end. So I hope that was helpful. If you have any questions, please come to office hours. Please reach out to us. Email, group me, whatever works best for you. I wish you all the best of luck studying this test, and I will see you all later and on test day.